here. Okay, does everybody see my 4.2 up there now? Yep, yes, yes or no? Can you give me one of these if you see it? All right, or a thumbs up, perfect, thank you. All right, so we're gonna be looking at mainly the sine and cosine and what effects some multiplicative and additive changes have on these functions. So last time, if you remember, we took the whole time pretty much to develop the graph of sine. We developed from the unit circle, we had some values, we talked about the domain, we can plug in anything, any angle goes into those functions, but it has to be in radians, right? Because radians are real numbers. So when we're dealing with functions, we have to plug those radians in. We only get certain values out. So remember, we were trapped on that unit circle. So we could only go up for sine as high as 1 and down as low as -1. So they called it the range. The range is from -1 to 1. And we did say, since those functions were trapped, we have an idea of the height of those functions when we plot them. We called that the amplitude last time. So the amplitude was essentially, if you look at the middle point of the graph, the midline we call that, it's the distance from the middle point up to the top or down to the bottom, always positive. But in this case, it'll be 1. Another way you can find it is taking the highest point, subtracting the lowest point, and averaging that. So the amplitude of these functions, the distance from the midline to the highest or the lowest point, would be 1 for sine and cosine. So cosine's trapped going left and right, correct? So the highest I can get is at 0 radians. I'm going to be at 1 for cosine. Then as I progress around to pi radians or 180 degrees, I'm going to be at -1. So we had the idea of the range or amplitude. The midline is going to be sort of the middle of the graph. And then we talked about how long it took to repeat itself, and that was called the period. So for those graphs, since once around the unit circle, whoops, I'm going the wrong way. Once around the unit circle is 2 pi radians or 360 degrees. Every time we go around that circle, the graph is just going to repeat itself. We find those values on the X and Y coordinates, right? So I want to check out and see what happens when we multiply those functions by a constant. So I'm going to be looking at these graphs of cosine and sine of X. I think we're going to be looking at cosine first. Yeah, so last time we looked at sine graph. Now we're going to be looking at cosine. And I want to see what happens to the graph when we multiply these graphs by a constant outside. So this is a multiplicative outside change. Multiplicative outside change. So I'm going to attempt to share my Desmos here, and I'm going to take a look at these 4 examples. So let me see if I can find that here. Okay, there we go. So do you see my Desmos now? Yeah, all right, thumbs up, great. So let's sort of think about this. So I have y or f of x is equal to cosine of x. It's that black graph there. So you do see what we have. So this is the different one that we plotted from last time, and we'll be looking at those other functions later. But for now, we want to get a good grasp on cosine and sine. So remember, for cosine, this starts out at the max because it's going to be the left and right behavior on that that unit circle. And as we spin around, it gets closer and closer to 0. And then it's all the way to the left point at 180 degrees. It's going to be at 0, 1, 0, -1, I should say. So 0 for cosine at 270 or 3 pi over 2 radians. And then when we spin the whole way around, we're back at 1. So this would be 1 period of that graph. You also sort of see this, what we call the midline, and it looks like an asymptote, but it's not an asymptote. This is sort of the symmetry of the graph, okay? So that midline is right there on the x-axis at y is equal to 0. We have high point of 1, low point of -1, so that's going to be our amplitude. The average between those, or the distance from the midline to the top or the bottom, is going to be 1. Okay, so now we want to sort of conjecture So we're going to be sort of experimenting around. I need your participation. I'm going to need your help. But some of this hopefully will be a little intuitive. If we make a mistake, hey, it's no big deal. This is just practice, man. It's class. So I want you to think of a function. Maybe it's been a while since you've looked at function, but you've all taken college algebra. A good graph that you've sort of worked with a lot is this parabola, right? So think of your f of x, or y is equal to x squared. Okay, we can think of it here. Ooh, okay, so what would happen if I went ahead and multiplied that by a 2? Would we know how that would affect the graph if we multiplied it by a 2? You can show me, or you can say it out loud. I just need some participation here.
It would stretch the parabola.
It sure does. It sure does. It stretches it. It stretches it out like this, right? Vertically. So nice job, Connor. That makes some intuitive sense, because what we're doing is if we have f of x, or y is equal to something, and we multiply that y value by 2 on the other side of the equation, it's going to take every y value and multiply it by 2, right? So we should see this graph being stretched by a factor of 2. And so, Connor, what would the amplitude be then? Would the amplitude stay the same, or would it change?
The amplitude would change.
Okay, exactly. So let's go ahead and plot it here. So I'm just gonna open this up. Bam, you're totally right on. Excellent. So what's the amplitude gonna be for this graph here, the blue graph? Two, yeah, exactly. So you see that it's stretched out by a factor of 2. So you might be able to see here that all the x values are going to be the same. So like when I was at x is equal to 0, my y was 1, but now it's been multiplied by 2. So the x values stay the same. The y values get multiplied. Oh my God, there's a party going on. Yeah. Who's having a party? Okay, thanks. Wow, it sounds fun where you're at. Are they having as much fun as we are? I don't think so. Okay, so, but notice here at 0, why doesn't it change there? 0 is still 0, even when we're multiplying by 2. Why doesn't it change?
0 multiplied by 0 is still 0.
Okay, that's true, but we multiply by 2.
Oh, well, 0 multiplied by 2 is still 0.
Yeah, it sure is. You're right. Nice job. So those zeros aren't going to change when we stretch this out. You're right. Excellent. So everything's going to be stretched out. Every y value is multiplied by 2, but the x values don't change. So in the case of the first one, we saw our amplitude was 1. Now our amplitude is going to change to 2. Awesome. Questions there? Okay. So now we're going to take 3 times that cosine. So Nicholas, what do you think is going to happen there?
It's going to stretch out even more.
It will. It'll stretch out even more. What will the amplitude be, do you think?
3.
All right. Well, let's check that out. Okay. Yeah, exactly. Yeah, I had no reason to not believe you there. And you're totally right. Nice job, Nicholas. So in this case, the amplitude is going to be 3, and we've seen it stretched out. So now, instead of at 1, it's going to be multiplied by 3. All the zeros are still the same. That's pretty intuitive. But we're seeing now that when we multiply the function by an outside multiplier, it's going to be affected vertically by a stretch. Now I have a constant here, 1/4. So that seems to be a little smaller. Jay, what do you think is going to happen when I multiply by 1/4?
It'll shrink
It'll shrink it down vertically, right? By how much?
by a factor of 1/4.
By a factor of 1/4, right? Or a factor, it'll shrink by a factor of 4, or it'll be multiplied. Yep, it'll be factored by a factor of 1/4. That's right. So what do you think the amplitude is going to be?
1/4.
All right. Nice job. That's exactly right. So these outside changes, they're nice because they're intuitive. Yeah, you can see that red graph there. It's been compressed by a factor of 4 or multiplied by 1/4. So it shrinks down just like Jay said, and our amplitude is going to be 1/4. Okay. So we can see what happens when we multiply the function by a number. If it's between 0 and 1, it looks like it's going to be compressed. If it's bigger than 1, it looks like it's going to be stretched out. Now I have a question for you, Jaden. What do you think is going to happen if it's negative?
I don't know.
Okay, let's think about it. This has been controlling the y values, right? So when we multiply by 4, it made the y value 4 times as much. What do you think is going to happen when we multiply by a negative? Where is that y value going to go if it's positive?
Is it just going to reflect?
Yeah, exactly. Nice job. It's going to reflect about the x-axis. Excellent. All right, way to go. Welcome, Grace. All right, so let's check that out. So I've created something here, my master plan, where I can actually move this function up down. So I've got my graph is a little polluted now. I'm gonna maybe hide a few of these things. So we're just looking at the green one. So we saw that when we multiply, really that constant, whatever the a is, it's going to be the amplitude, right? And that's going to stretch it out. Or if the a is between 0 and 1, it's going to make it compressed, just like Jay said. And Jaden said, like, if it's negative, let's see what happens if it's negative. Yeah, you're exactly right. It's going to be flipped about that x-axis. So if a is negative, we're going to have a reflection about the x-axis there. So we're trying to put all this together, and we're starting with these outside multiplicative changes. So I'm going to go ahead and do a new share. I'm bouncing all over the place today, but I think we've got what we needed from that. That's great. So we looked at these examples, and I think that we'd all agree, hopefully, that in summary, so this is from your textbook, the amplitude is just really going to change when we multiply the function by a factor. So it's an outside multiplier. That's what we call it. Outside multiplier. If we take a sine or a cosine times a, it's going to affect the range, right? So the range, the amplitude, not only did the amplitude change, but the range did too. So like when we multiply it by 2, it was -2 to 2. When we multiply it by 3, it was -3 to 3. When we multiply by 1/4, the only y values we could get out would be -1/4 to 1/4. Think about that unit circle and think about it getting smaller. So that's what's going to happen with a multiplier on the outside. And amplitude is always positive. So if a is negative, then as Jaden said, we're going to flip this graph or reflect it about the x-axis. It's shown right here in your notes. It's reflected about the x-axis. This is from the textbook. And the amplitude will be that absolute value of a. Okay? So that is an outside change. Are there any questions about outside multiplicative changes? It's pretty intuitive, right? I like thinking about it with the parabola. Oh, it's going to shrink or it's going to become wider, compressed. It's just going to be vertical compression or a stretch. Okay, great. So what else can we do? Well, I guess the next thing to look at is like, what happens if we multiply inside, right? So we can do inside changes as well. And here we're going to actually be multiplying but to the x. I want you to see this big difference here though, okay? With an outside change, I'm multiplying across from the y or across from the function. And when I multiply it on the other side of the equation by that a, it did exactly what I thought it was going to do. It stretched it if a was bigger than 1. It compressed it if it was between 0 and 1. With inside changes, with inside multipliers, we're multiplying inside, but we're multiplying directly on the x. It's not on the other side of the equation. So we're multiplying that x directly in this case. So now we're going to see what happens when I have an inside multiplicative change. So recapping amplitude, -1 to 1, we saw that an outside multiplicative change changes that amplitude. It changes the height of the graph. The midline, all those midlines were still at 0, right? Y is equal to 0. It didn't move the graph anywhere away from that. And the periods, I don't think it affected the period at all as well. So there were still 2 pi. So let's see what happens if we look at an inside multiplicative change. So I'm going to go back to Desmos. We're going to use cosine again. We're going to look at cosine of 2x, cosine of pi x, and cosine of 1/4 x. So let me see if I can share. New share. All right, so hopefully you're viewing my Desmos now. I need to find the inside multiplicative change. Okay. I'll find it, don't worry. There it is, inside multiplicative change. Okay. So here again, we have that graph of cosine. We have the same aspects. So we have the amplitude, we have the range is -1 to 1. We have that midline there on the x-axis, and its period, you see, is still going to be 0 to 2 pi. So you can sort of draw that in. So cosine starts at the top, as we talked about, and in 2 pi radians, it comes back and completes the cycle. All right, so let's think about cosine of 2x now. So now we're actually multiplying the x value. So when we multiplied across from the y value, that stretched our function vertically and compressed it vertically. Does anybody have any intuition about what would happen if you multiplied the x value by a number like 2?
It would stretch it horizontally.
Okay, so it's going to either stretch or compress it horizontally, right? Okay, and that's exactly what's going to happen. If you think about it, it should make intuitive sense, because what are we doing? We're multiplying that x by 2. So the y is not going to change at all. Y doesn't get messed with. It's just the x. So the x is going to change. The y is going to remain the same height, okay? Nice job, Connor. So this is going to stretch or compress it. Now we're talking about horizontally. So with 2x, so with y is equal to cosine of 2x, do you think this is going to be a stretch or a compression? We have to think about this. This is not as intuitive. If you remember from college algebra, the thing is that we didn't really discuss, like, it wasn't that important with these college algebra graphs if we had these horizontal stretches or compressions. It was more like shifting. But I'm here to tell you that if you multiply by a factor of 2 inside, that's actually going to compress it horizontally by a factor of 2.
Yes, I was right.
You were right? Okay, great.
Yeah, no, I was like, yeah, I only vaguely remember the college algebra, but I remember enough to know that the inside is like flip-flopped.
Very good, very good. You and your teacher get a gold star there. That's good. Like when I first saw that, I was like, mind blown. Poof, what's going on here? But then I sort of came to peace with it. So this is what I sort of thought, and I don't know if this will help you or not. Hopefully it won't hinder you at least. When I'm looking at these graphs, okay, so let's say that I wanted to, let's say that I had pi over 4. So that's 45 degrees, okay? So cosine at 45 degrees is 1 over root 2. If I plugged in pi over 4 for the second one and multiply by 2, hey, I'd already be at 90 degrees. So when I plug in pi over 4, I'm already going to be up at or down to 0. So what that means is I have to plug in half as much to get as far as I would from the original graph. So that's why it's actually compressing it. Another thing that sort of makes me come to terms with this is I'm actually multiplying directly by the x. So whereas with these outside changes, when we multiply and add on the other side of the equation, that's going to be very intuitive. When we multiply and add directly onto the x, that is counterintuitive. That's going to do the exact opposite of our intuition. But the reason why is because it's going to sort of speed up that graph a little bit. So let's just take a look at that. Bam, look at that. So now it looks like it has sped up that graph and it's compressed it by a factor of 2. What's the period of that graph now?
1 pi.
Now it's gonna be half as much. So it's sped up, so it's going twice as fast now. So if I took 2 pi units to trace that out, now it's going to complete 2 cycles. Good. So this speeds it up, and now you see that if I trace the graph, its period, it's going to be exactly pi units. Nice job. So what we see in here is this didn't affect the amplitude at all, but this will affect the period. So if our regular period here was 2 pi, when I multiply by 2, that sped up the graph, and our period now is going to be pi. Okay, great. Let's look at another one here. So now I'm going to go ahead and multiply it by 1/4. So Ching, do you have intuition on what you think is going to happen if I multiply it by an inside factor of 1/4 there?
It's gonna compress that.
Okay, so will it compress it? So if I plug in, like, let's say a pi, and if I divide it by 4, I'm actually going to be at pi over 4, where the original graph was at pi. So instead of compressing it, it's going to
shrunk, like
it's going
shorter.
it's going to actually stretch it.
Stretch
So,
it.
yeah, so this is going to be counterintuitive because we're between 0 and 1. So now if I plug in something like, let's say 2 pi to the first graph, the black graph, then it's going to be the same thing if I plug in what for this y is equal to 1/4 x. When will I get cosine of 2 pi? I'll have to plug in what?
1/4.
Well, if I plug in 2 pi here, I'm using my mouse, so it might not be the best. Here, let me just, there we go. If I plug in 2 pi here, what do I have to plug in for x to get 2 pi for this whole thing?
2 pi. I'm not sure.
What about 2 pi times 4? What about 8
2.
pi? So if I plug in 8 pi, 8 over 4 is going to be 2 pi, right? Okay, so now what you can see here is that I get the y value for the first one at 2 pi, where it's going to be 8 pi for the next one. So it's going to stretch out. In fact, it's going to stretch out by a factor of 4.
Okay, so it's expanding.
It is. So we call that a horizontal stretch. Look at that graph. Okay. What would the period of that graph be now?
That's cool.
Yeah. So can anybody help us out with the period?
8 pi.
Yeah. So this thing is stretched out. Sorry. Thank you for helping us out. This one's stretched out to 8 pi. You can see that I need to use that whole, sorry. I need to use that whole graph there just to get that one period in. So I go 4 pi to the left and 4 pi to the right. So this one has a period. It's been stretched out by a factor of 4. So when we have an inside multiplier that's between 0 and 1, that's actually going to stretch it horizontally, right? But when we have an inside multiplier that's greater than 1, that's actually going to compress it by that factor. So it's totally counterintuitive to the stretch and compression of vertical. So the horizontal stretches are totally, they're totally counterintuitive. Are there questions there? Okay. So maybe you see a pattern of how to get the period, because we want to figure out how to get that period by just looking at that number. They call it b that they multiply it by. So does it jump out to any of you to see how you would get that period just by looking at that number b, how you would get that? So the number b is actually the multiplier. Down here.
Would you take 2 pi times the inverse of the inside multiplier?
Exactly. Great. So to get the period of a graph like y is equal to cosine bx or sine bx, it works the same way. You're going to take 2 pi, and when you said inverse, what I interpreted was that you were taking the reciprocal. You were dividing it by that b. So for instance, when we look at that blue graph, that period is going to be 2 pi over the b, which is 2, or pi. This one here, this one's going to be 2 pi. So it's going to be a regular period, 2 pi, that they have without any multipliers, and we divide it by that constant in front. So 2 pi divided by 1/4, 2 pi times 4/1, that's 8 pi. So I want you guys to think about cosine of pi x. I'm going to give you a minute here. What is going to be the period of cosine pi x? Don't say it out loud. Type it in the chat and wait on it for a minute. So I'll give you a minute. So what is the period, do you think, of cosine pi x? Think about that one, please. Okay. Good, looking like most of you are ready. 1 second. All right, so we're looking for the period of that cosine of pi x. I haven't revealed it yet. We're waiting for the big reveal. Okay. You ready to share? Yeah, okay. Let's do it in 3, 2, 1, send it. 8, okay, you are ready. All right, good. 11, 12. Wow, that's almost everybody. There's only one more person. There it is. Okay, let's just check. 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Wow, you guys are on it. That's exactly right. So the big reveal. If I just clear all this out and maybe even turn off these, you'll see that when I reveal that, yeah. So since pi is greater than 1, it's 3.14 or something, it has been compressed. So in fact, it's going to make that entire cycle in 2 units. Now remember, to get to 2 pi, that's a little over 6, right? So this does look like it cycles through 3 times plus a little bit more to get to 2 pi, right? Okay, so that's a period, that's right. Okay, what do you think is going to happen if I make my b negative? What do you think is going to happen there? Kai, I saw you saying something. 2. Oh, wait, do that again. It's gonna be a reflection, right? A reflection across which axis? Show me with your fingers. Oh yeah, there we go. The x-axis. No, wait, that was the one that was with the outside change. Oh, okay, the y-axis. There we go. All right, yeah. So this is going to reflect it about the y-axis if b is negative. And if you think about it, it should make a lot of sense because again, the y value is not changing, but when I plug in x, if that's negative, then it's going to make it negative x. So it's going to flip it right over, reflect it right over the y-axis. You got it. Now, here's the deal with cosine, though. Cosine, we talked about sine being an odd function, but cosine's an even function. So when we make this be negative, it's not really going to seem different. It will flip over that axis, but it's going to look very similar, in fact, the same. So cosine, just like sort of the squaring function, the parabola, they have symmetry with respect to the x-axis. So when I have, or with the y-axis, my bad. So when I have a function like that, it will flip it. It is flipping it about the y-axis, but it's really looking the same. So the way that we talked about an odd function last time, f of x equals to cosine is an even function, where it's even. And what that means is that it has y-axis symmetry. And mathematically, what it means is that if I compute the function at a negative x value, I will get the same thing as if I computed that function at the positive x value. I can show you that sort of graphically. Let's just pick on this point here. So this point has coordinates. If I go over x, it's going to have an f of x value or y value that's this high, right? Now, if I do a negative x, and if I compute f of minus x, I look on the graph, my y value is going to be exactly the same place. They're going to be equal. And that's true for all these. So if I'm like over here, at these y values here, it's going to be the same across here. So what that means is if I have, for instance, a cosine of negative 2x, that's going to, I can replace it by a cosine of 2x. All right, so this graph here will be exactly the same as that graph there because cosine is an even function. So I've doubled my productivity. Like if I have a mastery test, or if I wanted to find the cosine of negative pi, be like negative pi, well, that's just going to be the same as the cosine of pi. So the cosine of pi, I think, let me see, cosine of pi, negative 1. So that's going to be the same as the cosine of negative pi. And you can sort of see it there. There's the negative 1 for cosine of pi, and there's the negative 1 for cosine of negative pi. So with these even functions, we can do that. We can replace the function of a negative value by the function of the positive value. And it turns out like all these trig functions that we study, they have some sort of symmetry like that. They're either even or odd. We talked about last time that sine was odd. What that meant is if we took f of negative x, then it's going to be the opposite of f of x, but cosine's even. All right. So let's go ahead and sort of summarize what we've been doing here, unless there's questions. I'm going to wait a minute for questions here or a second. Any questions there? All right, let's go ahead and summarize then. New share. So now we see with these outside multipliers, that's going to control the period, and it's going to be, so the inside multiplier is going to control the period. It's going to be a horizontal stretch or a horizontal compression of the graph. So in general, if we have the period that goes from 0 to 2 pi for the original graph, if we divide by b, then the new period will be from 0 to 2 pi over b. So that 2 pi over b will be our new period. That'll be the amount of time it takes for the graph to repeat itself. And you can see by that calculation, if b is between 0 and 1, then that's going to be more than 2 pi, the period. If b is greater than 1, it's going to be less than 2 pi. Again, periods like amplitudes are always positive. So if our b is negative, we just assume that it's the absolute value. Okay, and so the things that we've learned so far is if we have an outside multiplier like an a times sine of bx, then our a is the amplitude, the absolute value of a is the amplitude. 2 pi over b is going to be the period there. So we've learned all about multipliers, outside and inside multipliers there. So there are two more things to discuss with the aspects or attributes to this graph, these graphs, and that is going to be additive changes. So that's sort of a discussion for 4.3. So now we're going to be sort of looking at the sine graph a little bit. We've exhausted the cosine graph, but that's good that we look at both of them. We're going to go back to look at the sine graph, and we're going to see what happens if we add something on the outside. So if I just take something and add it on the outside, like, okay, what's going to happen in that example? So again, thinking here, we're adding that k value across from the f of x. So we're adding the k value onto the other side of the equation. So let's look at this first one. Number 1, f of x is equal to 2 sine of x plus 3. So Sean, what do you think that plus 3 is going to do intuitively to that function?
It will go up 3.
Exactly. Great. So this is totally intuitive. We're adding on the other side of y. So it's going to take our graph and it's going to move it up 3 units. So again, outside changes, totally intuitive. We're adding on the other side of y. So it's just going to be equal to what we add on to y. Now, Sean, there's another thing out there. There's a 2. What does that 2 do to the graph?
That's the one that will stretch, right? That will stretch the
Right.
graph.
Yep, it's going to stretch it vertically. So we should see it stretched vertically. That's going to change our amplitude. What's our amplitude going to be, Sean?
2.
2. Great. And you know that midline hasn't changed at all, but now it's going to change. So the midline's going to, let me
3.
see. It's going to go up 3, exactly. So now it's going to be y is equal to 3. So let's go ahead and see that. Nice job, Sean. So let me see here. We're looking at additive outside changes, are we now? Whoa, okay. Additive outside change. There we go, outside out, same thing. Okay, so there's the graph of sine. It looks a little bit different, right? So we start at 0, we go over to 2 pi, and it has an amplitude of 1. But if we look at this graph, yep, it's been moved up 3. It's been stretched out 2 by a factor of 2. And if I look at the midline here, so let me see here. Let's just say that k is equal to 3. And turn that on. Our midline has shifted up 2, or shifted up as well, not 2, but it's shifted up 3. It's shifted up as well. So this is going to help us with the attributes of this sine graph. So, and cosine. This is going to be a lot like your Desmos project. If you get an early start on the second one, we're sort of talking about what happens with the outside changes. So we can see that the multiplier is going to affect the amplitude. That's going to affect the amplitude. So the high to low point, it's also going to affect the range. So we're really going to be in that project looking at the range. So now our range has, when we multiply by 2, it's gone from -2 to 2. But then we move it up 3. So when we move it up 3, what is our range now? Can you finish it out, Sean? So what's our range for that blue graph?
After we move up 3 or the
After we move up
original?
3.
Okay, so it's going to be 1 to 5.
Exactly. Excellent. Nice work, man. All right, so it's going to be -1 to 5. -1 is going to be it's going to be the smallest we can ever get out. 5 is going to be the biggest. And if you think about this, you can take the midline and then subtract 2. So 3 minus 2 is 1, and add 2 the amplitude. 3 plus 2 is 5. So that's what you're going to be sort of looking at with that project. Questions there? Okay. So let's look at minus sine x minus 4, minus sine x minus 4. Okay. Minus sine x minus 4. So let's talk about the negative out in front first. Logan, do you know what's going to happen with that negative out in front, the negative sine x minus 4?
It's going to move down.
Okay, so what's going to make it move down? You're right, it's going to move down.
The negative sign.
That will actually do something
Wait,
else.
I'm confused. What's the question?
I was just asking what the negative sign was going to do.
Oh, it's going to flip it. Sorry.
Yeah, there you go. It's going to flip it. You got it. And then the -4 is going to
Move it down.
move it down. Excellent. You got it. Sorry about not stating that more clearly, but nice job. That's exactly what's going to happen. So that negative out in front, that's going to flip it. Not going to change the amplitude though. The -4 is going to move it down 4. So where will our midline be, Logan? Where should I put our midline in at?
4 or -4.
-4, perfect. All right, let's check that out. Whoops, whoa, what's happening? Don't do that. My bad. And then let's go ahead and turn this on. Yeah, perfect. So you can see that the graph is definitely flipped. It's reflected about the x-axis because this high point now becomes a low point. And the shift really controls the midline, right? So if I shift it up or down, that midline is going to be shifted up or down as well. All right, finally, Logan, for the win, what's the range going to be? What's the range? What are the possible y values we can get out?
-3 and -5.
Okay, excellent. So we always go from lowest to highest. So I would say -5 to -3, but you got it. Nice job. Way to go. All right. Questions there? It looks like you're getting this. So the outside additive change is going to move it up or down. Totally intuitive. All right. Nice, nice, nice. Way to go. Okay. So I want to try to give you a chance to create something. So I'm going to go back and share this. I want you to write the equation of a function of y is equal to sine of x with an amplitude of 3, a period of 2, and shifted down 1. So I'm going to give you a couple minutes to think about it. Don't blurt it out, but type it in chat. And then in a couple minutes, I'll have you send it. So we want to try to find the equation. So we're putting it all together. So the function of y is equal to sine x. So it's going to be y is equal to sine x with amplitude 3, period of 2, shifted down 1. So it's going to be y is equal to blah, 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 sine of blah, 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 x, plus or minus blah, blah, blah. You have to fill in those blah, blah, blahs. So see what you can do there, and then we'll check it out. It's going to be exciting. All right. I'm excited at least. All right. So go ahead and think that one over. feel like Mr. Tom Petty, the waiting is the hardest part for me, maybe. But I want to give you time, so keep going. All right, so amplitude of 3, period of 2, shifted down 1, y or f of x is equal to something, a sine and something, something. Put it all together. All right, so enter it in your chat. Few more seconds. All right, we're gonna have the big reveal in a minute, but let's see what you guys think. So hopefully you have a good idea. And 3, 2, 1, send it. All right. Okay. So I think I gave most of you enough time. That's good. Got 9 there, 10, 10, 11, 12. Well, that's darn near everybody, but 13 would be perfect. I see you all there. Someone's not just there, not there yet. Let me get people a chance. There it is, 13. Okay. 3 sine pi x minus 1. 3 sine pi x minus 1. 3 sine x minus 1. Wow. Okay. So almost everybody agrees on the 3 and the -1. Whoa, there's a fancy pi. How did you get that, Sean? Is there a symbol that you put in there?
I just copied it off the internet.
Oh, nice. All right. Fancy. So, okay. So let's just take a look here. So almost everybody agrees with the amplitude, 3. So that's the outside multiplier. Great. Everybody agrees with the -1. So that's an outside change. We subtract 1. The period, and this was the same as my first class, that's sort of the thing that might trip people up. So let's just talk about how we would find period here. So I'm still sharing my screen, right? Yeah, okay, thank you. So my period that I want is 2 pi, or sorry, 2. But how do I find the period? It's going to be 2 pi over that b, which is multiplied by the x there. That's the inside multiplier. So if I sort of set up an equation, maybe put the 2/1, take the cross product, so like 2b is equal to 1 times 2 pi, and divide by the 2, then Sean and the other ones that had pi in there are correct. Nice. So your function should be exactly f of x is equal to 3 sine of pi x minus 1. All right, let's check it out. Nice job. Nice job. So, okay. And it looks like, you know, if I want to even get fancy, I can move that midline down to -1, right? It just goes with the shift. So let's go ahead and use these sliders. So A was 3. Oh, I have to plot this. Okay. A is 3. There we go. K, that was the shift down 1, so -1. And B was 3.14159. It was pi. So that's speeding the graph up. There we go. So that is the graph that you would get with that y is equal to 3 sine pi x minus 1. So it has shifted that black graph down 1. It's stretched it out by a factor of 3. And then it's caused the period, it's compressed it horizontally. It's caused that period to really speed up, right? It's going to have like 3. Hold on a minute. It's going to have how many cycles? Well, let's see. 1, 2, 3. Yeah, so it's going to have 3 at least 3 cycles in there before we hit 2 pi. So it has compressed it quite a bit. All right, so that is sort of putting that together. Are there questions there? I want to make sure that everybody's sort of clear with what's going on. All right, well, that leaves us with one more thing to do. And that's what happens if we sort of add things in. So we're going to be adding things inside. We're going to do an additive inside change. So first of all, summarizing, they put the k in the textbook out in front, like k plus sine of x. That's the same as sine of x plus k. So k moves the graph up or down, and it moves that midline up or down as well. If k is positive, it moves it that many units up. If k is negative, it moves the graph that many units down. Okay. So the last thing we want to check out is what happens when we take these graphs and do an additive inside change. So an additive inside change. Let's go ahead and take a look at sine of x, but now it's going to be sine of x times, or sorry, minus additive, minus pi over 6. So intuitively, what do you think is going to happen with that additive inside change? You don't have to tell me exactly what happens, but what would happen overall? Do you know, Caleb? Intuitively, what would happen?
I'm not sure.
You're not sure? Okay, that's okay. Cole, what do you think?
I'm not sure either.
Okay. Allie?
I don't
Not
know.
sure. Okay. Grace. Let's give everybody a chance here. It's going to move it to the left or the right. Yeah. So intuitively, if an outside change moved the graph up or down, when we added it on, wouldn't an inside change, we're adding onto the x, move it to the left or the right? Well, it does. But the thing is again, this is going to be counterintuitive. So when I subtract pi over 6, which way do you think it's going to move it, Grace? Oh, I don't think your mic's on. Sorry. Or you can type it in.
She's saying left. It's just really, really soft.
Oh, okay, got it. So it does seem like it would move to the left. Thank you for saying that. I'm hard of hearing anyway. So it does seem like it would move to the left, but inside changes are counterintuitive. So this is actually going to move it to the right, pi over 6 units. But how do you sort of make that work in your brain? This is the way that I do it. So I think of 0. So if I wanted to get sine of 0, and it was a normal function, I would just plug in 0 for x. But for this function, what would I have to plug in to get sine of 0? I'd have to be all the way to the right, pi over 6, to start that function out, right? So I'd have to move to the right, pi over 6, just to start that out at 0, because pi over 6 minus pi over 6 is 0. That helps me make sense of it. But if you can remember, anything in the inside, when I'm talking about inside, it's inside the parentheses. If I multiply that x, or if I add or subtract that x, it's totally counterintuitive. It works the same way as the outside changes, but it's just it's counterintuitive. It goes the reverse direction, okay? So also notice I'm just adding right onto the x. I'm not adding across the equation. So that makes a little bit more sense as well, at least to me. So with that in mind, the sine of x plus pi over 4, which way and how much should that move? I don't know, Caleb. So when we have sine of x plus 4, which way and how much would that one move?
It moved to the left pi over 4 units.
Exactly. Exactamundo. You got it. So this thing's going to move, nice job, Caleb, to the left, pi over 4 units. Okay. All right. Finally, you could have multiple inside changes. And this gets a little bit more complicated. So what I would suggest, if you have some additive change inside those parentheses, so some additive inside change, what I would suggest, if it's not already, to factor out what's in front of the x, so we can find that change. So really, when we're looking at this one, this could have been represented, it could have been given to you like this, okay? You could have had the same thing as sine of 1/2 x minus 1/2. So if it's like that, what I would suggest to do strongly is take out that common factor out in front of the x, and then you can think of it in 2 steps. So if you look at it how it is here, first of all, we can interpret that as a sine of x minus 1. So if we have the x minus 1 change, which way and how much does it move that graph, Cole? So sine of x minus 1, is that going to move it to the left or the right one?
To the left one.
It's counterintuitive.
And to the right.
Exactly. Good. So this one's going to move it to the right one unit. Nice. And what's going to happen with that 1/2 on front? So that's also added on there. So that's a multiplicative change. Ali, do you remember what happens when we multiply by an inside change like that 1/2?
They get smaller.
Yeah, so it's going to change that period, right? So good, it's going to change the period. Instead of being 2 pi now, it's going to be how much?
Would it just be pi?
So we're dividing by 1/2, so that actually flips it up and makes it 4 pi. Okay, so since we were inside change and that was between 0 and 1, everything's counterintuitive. So instead of making it, compressing it horizontally, it actually stretched it out by a factor of 2 there. So I know it's difficult, but once you get practicing, you're going to get into this. If you have an inside change, it's going to be totally counterintuitive, but the period will change by 2 pi divided by whatever that multiplier is inside. And when you're adding or subtracting inside, if it's subtracted, you move to the right. If it's added, you move to the left. So this one should be the sine graph with a period of 4 pi, so it's stretched out. And that whole graph is moved 1 unit to the right. Okay. So before I show you these, let's just talk about what we learned today. Okay. So when we have a graph of y is equal to sine bx plus c, so this is totally inside change. We just sort of looked at this. You don't have to really worry about the phase here. They talk about that somewhat later, like in later classes, but we're not going to worry about the phase. We're going to talk about the period. So the period is always going to be 2 pi over that inside multiplier. It's always going to be positive. The horizontal shift will always be what we add or subtract directly from the x. So what I was saying is, you know, if you have a bx plus c, then what you should try to do is factor out that b first, and then you're left with x plus c over b. Just remember, by distributive property, you can distribute that back in and get the same thing. So this is going to move it horizontally, negative c over b. That's why that's generalized like this. Okay. So putting it all together, if you have a graph of sine or cosine that has been shifted like k plus a times the function, b times the quantity x minus h. A is always the amplitude, vertical stretch or compression. B is always going to control the period, horizontal stretch or compression. H, the inside addition, is going to move the graph left or right. It's counterintuitive. So if h is positive, it moves it left. If h is negative, it moves it right. And then the vertical translation it's going to be just like your intuition. If k is positive, it moves it up. If k is negative, it moves it down. In addition, if a is negative, the graph will be reflected about the x-axis. All right. So that was a lot of stuff, but that was all we went through today. All right. So let's take a look at that last slide there with and sort of verify our results. So I need to go to my inside additive change. There we go. Right at my fingertips. So we said when we have sine of x minus pi over 6, that should move it to the right. Okay, there we go. So it moved that graph of sine to the right. Counterintuitive. This one has a 2/3 times it. So this amplitude must have smashed down a little bit. So the pi over 4 plus pi over 4 moves it to the left. Very good, as Caleb was saying. And the 2/3 that's been put on there is actually going to shrink the amplitude a little bit. Okay, so you can see that that's actually been moved pi over 4 to the left, and the amplitude's been smashed down a little bit. Now the last one you see there should be should affect the period. So the period here, it should stretch it out by a factor of 2. So the period should be 4 pi, and this should also be moved over 1 to the right. And so you can sort of see that. You can see that move maybe over to the right 1 unit. So 1, it's a little over pi over 4. Pi over 4 is 0.707. So it's been moved over 1, but it's been stretched out too. So in fact, it's going to take 4 pi to take a period of that instead of just 2 pi. All right. So those are a lot of attributes about the sine and the cosine graph. Hopefully that will help you out there. I also have that Desmos project, which you can start on whenever you'd like. Make sure that you finish the first one up if we didn't finish it in class with us by Thursday. And this next one is going to be due actually by next Tuesday. And remember, with Desmos, you don't have to submit anything. You can go back and revise things until the deadline of the next test, which is next Thursday. Or no, actually that's the mastery test, my bad. So the deadline is on there. Okay, if you have any questions, please feel free to stick around. Otherwise, nice seeing you today. Good job.